Okay, perfect powers in the Fibonacci sequence. Well, perfect power meaning a to the b, where the exponent is bigger than 1, is the only known ones is the numbers 1, 8, and 144. For the Lucas sequence, the only perfect powers that are non-zero, always non-zero, is 1 and 4. Actually, there is no 0 in the Lucas sequence, so not a worry. For the Pell sequence, the only perfect powers is the number 1, so quite boring. And for the associated Pell sequence, in other words, the numerators of the convergence. Let me just give the initial conditions. Usually the Pell-Lucas sequence has a 2 and 2 here, but then if we do the recursion, we're going to get all even numbers mod 2 mod 4. We're never going to get a perfect power. So because it's going to be a composite number, so it won't be a perfect power. So I mean, like this thing, sorry, the A can't be composite, but I'm just saying if it's to a certain power, we only have one single 2. So it doesn't matter. This exponent can't be greater than 1 if I have only one single 2 in the value A. So we're going to do this version. And this version is called the associated Pell sequence. And actually, if you look at Cauchy's book on the Pell and Pell-Lucas sequence, this is what he calls the Pell-Lucas sequence. I talked to him about that. He said the 2 is basically a nuisance factor, but then of course, it's really important to have these be the correct ones, 2 and 2. Many people in the audience here have told me because it's a Horodom sequence and that's historic, and there's a lot of results when this is 2 and 2, and it's just, so I'm not gonna call this the Pell-Lucas sequence with these initial conditions. I'm gonna call it associated Pell. So the question is, do we have any powers at all in this sequence? And that would be, if you can resolve that, then we can figure out that my research problem that I'm doing here. Then we can figure out under what conditions of the subscript n do we have that. There's a lot of connections between like this problem I'm asking and how that helps me do this problem. But I just want to resolve that there's no more perfect powers. We don't think there are at all. And what reason do we have to go on that? Well, lots of Mathematica telling me, factoring these numbers and nothing's happening. So, yes?
I'm just curious what the techniques are to prove that there are more perfect powers. Is it just elementary? The proof for this one, well, okay, so in the early 60s, they proved there was only, that for perfect squares was only 1, and then perfect cubes was done separately. And then to find out that there was squares 1 and 140, it was a paper in the Annals of Mathematics. It was really deep. I believe it's, the authors, but it's like 60 pages, and there's a lot of like Frey curves and all this crazy math that you wouldn't understand. So sorry, that we wouldn't think you need to prove that, but most of that was proving that there's no more. It's trivial proofs to prove that these, existence. Yes, but and so there's a 1-page proof for this one. So Cone 1964 1-page proof. So there's a reason why this might be reasonable to think that there's something trivial. And you're probably gonna ask, well, did you look at that 1-page proof and see what you could do? I think I did. I don't know.
So while we have here, a couple of questions. Is it trivial to prove using machinery from algebraic geometry that there's only finitely many solutions?
Don't know.
Okay. The second one is, can you modify this and ask about being, say, within a fixed amount of a perfect number? So if we be within
close
1,
enough.
like 5 is within 1 unit of a perfect square.
There's a number of papers, well, with this one being within 1 of a perfect square, maybe those also. But how would that help if we're really close to a perfect square?
It just might be interesting, if this problem is hard, could you take maybe even growing intervals and see what percent of numbers are within
near perfect square?
Yeah, and then the other thing is in terms of just getting a feel for problems, you can often do heuristic calculations. You can assume maybe the probability of being a perfect square, you know what the density is. If I just choose a number at random, the probability that it is a perfect square is just whatever that number is, treat it as a bunch of independent random variables, calculate the expected value of the sum of the expected values, and that would allow you to predict how many times you expect to get a perfect square or cube in these exponentially growing sequences. And because these sequences are growing so rapidly, my guess is you'll probably get sums that converge, and at least heuristically, you should be able to show that there are only going to be maybe finitely many. And then there might be some stuff in algebraic geometry, because a lot of times there's only finitely many integer solutions to certain equations. You might be able to get something like that.
Yeah, I forgot to say something that Jürgen Skoker, my collaborator, has proved that there's no cubes here, and he's almost got it down for no squares here, but there's infinitely other b's. But maybe if we can use the fact that there's no squares or cubes to prove that there's nothing higher.
Right.
That, so you can maybe bank on the fact that if we can prove that, just say that there's no squares and no cubes, can you use that information to show there's no other higher powers? I mean, take that as true, even though he doesn't have the squares thing yet. And yeah. Okay, that's it. So clap for open copies?
Yes. So this is fourth time.
Yes.
Oh.
Although I will say that for your previous talk, you got 3 rounds of applause, and this one you only got 1.
Well, I
That is
know Rigo 1.5 for those 3.
Okay, that's what I'm saying. This is a huge, like the Great Depression crowd. No, the reason we clap for something like this is the whole point of conferences like this is not just to present the math we've been doing, but to generate more collaborations. And so I love it when conferences have problem sessions so that we're encouraging, hey, these are things I'm thinking about. Is anybody interested in joining? And this is why we will write up the problems, and we will actually include this in the conference proceedings. This is how you do it. And odds are we're not going to be able to solve exactly what you wanted. Oh, we are. Never mind. Okay, got the solution already.
There is none.
Just get here's the block.
Well, it looked like a square.
Nobody will.
What's up?
But no, but again, this is the entire point, is we want to try to increase collaborations. Even if we can't solve this, maybe this will resonate with you. And hey, wait a minute, I know something similar to this where this might actually work. And I know some stuff, and if you want to email me, well, I'll try to find the stuff. There is a lot of good results, but there are only finitely many solutions in certain cases. Now, the problem is you have infinitely many possible powers, but it may not be too hard to show that for fixed B, there's only finitely many solutions. How finite is finitely many is a different story. But heuristic arguments, you can prove very easily there are approximately 3 Fermat primes. There's actually 5, but heuristically, you can show the expected number of Fermat primes is about 3. And I think those arguments will give you what the truth is. It just won't give you a proof of the truth. So let's give our speaker. Oh, sorry.
Okay, technically, we only care about the A values that are prime of the form 4k plus 3.
Okay.
So that's really all that we care about.
I was going to give you another round of applause, but you interrupted me, so I'm not going to do that. All right. Who else would like to present a problem? And it could be a problem from your talk and just repeating it so that we record it. All right.
Presenting briefly what
Absolutely. And
I'm
again,
presenting on is kind of related to Fibonacci.
right, yes. And I've got to say, you state your name when you're presenting. All right, so we are recording it, but you state your name. I think you're on now. You're on? Yes, and then you're in there.
Okay, I'm Giuliano Romeo, and my research is on continued fraction that have been presented in the last talks. So continued fraction is an expression like this that can be infinite at the denominator. And so a beautiful stuff is that if I have an algorithm, for example, I can make this rational, I just take out the integer part, that is, so this is 5, and I invert what is left. So this is how I get the 1 plus 1 over 2, okay? This is how I get the expansion of a rational number. And there is a beautiful theorem by Lagrange that has been exposed in the last presentation. It is that if alpha is so this can be proved. Has not been proved by Lagrange. But alpha is irrational if and only if alpha has a finite continuous fraction. Yeah, it's quite obvious here, but we have to remember it. And alpha is a quadratic irrational if and only if alpha has a periodic, ultimately periodic continuous fraction. This means that for rational numbers, for example, I don't know, square root of 2, for which we have an infinite and never periodic expression that is 1.414, never repeating, we're going to express it in a beautiful way that is just 1, 2 periodic. It means that this is equivalent to the continuous fraction 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 and so on. So we are expressing an irrational by means of 2 integers, and we know exactly how to write it. So, for example, to link it with Fibonacci, the expression of the golden mean. No, actually, yes, this is the golden mean. Is 1. And I think it's beautiful. That's just 1 plus 1 over 1 plus 1 over 1. Okay. The problem I work on is to find an optimal algorithm to obtain these 2 properties in the field of p-adic numbers. The field of p-adic numbers is obtained as the completion of the rational numbers, but not like R, but R is obtained completing Q with respect to the Euclidean norm, and p-adic numbers are obtained completing, in the sense of all Cauchy sequences are convergent, with respect to the p-adic norm that we have largely seen these days, and is the set of all p to the k plus 1 to the p plus a0 plus infinitely many powers of p. Of course, here there are precisions. The problem is that we don't have an algorithm in QP that respects these 2 properties. So I'm trying to find a correct algorithm. What does it mean, a correct algorithm? Because here, what we do, we take out the integer part. I write here, integer part. There's something left, and I invert it. And then I take the integer part and I invert it. So I have to do just 2 operations, taking the integer part and invert it. Okay? This is a field, so I have a unique inverse, so this is not a problem. The problem is to define well an integer part, because we don't have an obvious choice. There have been at least 4 or 5 choices in the history since the 1970, okay, when they have been first defined. So a problem, whose it would be great to deepen and to study about, and I'm studying this, is to find the beautiful integer part to apply to number of this form to obtain these 2 properties. Actually, there are some, and with my supervisor, I have defined also some algorithms that respect these first properties, because it's not free. There are p-adic algorithms that don't have the finiteness for all rationals. But the difficult part, and it's another problem, is to define a p-adic algorithm to define continued fractions p-adically that gain these properties. So this would be a problem, and it would be great to obtain this is the Lagrange's theorem. Actually, one verse is easy. That is a periodic continued fraction is solution of a quadratic algebraic polynomial. And this verse has been done by Eulero. The beautiful verse, the beautiful, I don't know, direction is the to give a periodic expression to each quadratic irrational. So if you take every quadratic irrational, you can have a periodic expansion. So you can, I don't know, domesticate it. I think it's beautiful. So this could be a problem if you want to read some work. You just type periodic continued fraction, you can find, I don't know.
Yes, thank you. Any comments? So I'll just say a few comments. First, one of the things you learn as you get older is that if you choose the right statistic, you can justify anything you want in life. And so the golden mean is in some sense the most irrational of all irrational numbers. It's the one whose rational approximations are the worst for given size denominator. So this is a wonderfully special number. Do you expect some kind of generalization of the golden mean to arise and stuff like this? In terms of maybe numbers which have interesting properties?
Yeah, you mean the expansion of the golden mean?
Which has the simplest expansion here.
Yeah.
And it has some wonderful properties. Are you expecting maybe some generalizations of the golden mean or other stuff to have some interesting properties in your periodic?
Yeah. There are some fields because it depends on the P,
Right.
on the field that I'm considering, where the golden mean has exactly this expansion. The thing is that we don't have only integer here, but we can have also rationals. So it could be also an expression of 3/2, 1/1/5, plus 1/3, plus 1/. Okay, so it's more Diophantine approximation. So we approximate irrational numbers by rationals that are integers, of course. And yes, it depends on the field. Not everywhere it has this beautiful expansion, the golden mean,
Right.
but somewhere, yes, it depends on the properties of P.
So the other comment is this your beautiful interplay between quadratic irrationals and your periodic continued fractions is one of the wonderful properties of continued fractions. The rational numbers have finite continued fractions. The quadratic irrationals have periodic. And then a big question is, well, what if I give you a cubic irrational? Is there something nice you can do there? I believe this is called the Heuristic problem. There are people who are trying to find alternate continued fraction expansions.
Multidimensional.
Multidimensional. And they have the same issue you have, that it's not well defined as to exactly what you're doing.
Yeah.
And that you have lots of different choices, and which choice is going to lead to something attractable and interesting.
Yeah. It's a big open problem in the real field.
Yes.
To have an analog of this theorem.
Yes.
For there are results that are quite near. This was a problem from Jacobi to find alpha cubic irrational if and only if the multidimensional continued fraction is periodic, but it has not been solved, has not been proved, and it is believed to not be true because some continued fraction have a very long expansion. So if you can find the period in, I don't know, 5 million, you suppose it doesn't have. Basically, multidimensional continued fraction has this structure, not only at the denominator, but also at the numerator. So and you can expand, them also in this, and there are 3-dimensional, 4-dimensional, and dimensional for cubic, partic, and all the rationalities. So there has been also some work on periodic multidimensional continued fraction, but I have not seen them yet.
Right. Given that we're having enough trouble with just the general periodic.
Yeah. And that's it.
Okay, thank you. If someone else would like to pose a problem. Good, I'm glad you're doing it when it's not your turn in the cycle.
See, you have to think.
I take minutes in real time for certain committees I'm on, and I actually write up some of my things beforehand so I can.
Oh, I've done that.
Yep.
Okay, so I have a mystery, and it's a mystery that emerged very, very recently. And so I need a little bit of background. So everybody knows what a partition of an integer is.
So partitions into parts. Yeah. Oh, yeah, I'm saying. So partition lambda is a sequence. And that's L, and we say partitions n, which is going to be the sum of the lambda i's, and we don't care about order. And so it was recently proven in 2017 that if you count the number of parts in a congruence class, so this is going to be the counting function of the number of parts that are congruent to R mod T of lambda dividing m. There we go. Sorry, this is a little bit hard to say. Over lambda partitioning n of the number of, I'm going to say this out loud as well. Yeah. Okay. Yeah, so this means lambda partitions n.
It's like a sign.
It's called a B dash. And yeah, our turnstile. So what this counts is the number of parts among all partitions of n, which are congruent to R mod T. Okay, and the theorem that Beckwith and Mertens proved is that this is equidistributed in the limit. Namely, TRT n over TSTn goes to 1 as n goes to infinity for any R and S. However, they proved something more amazing, which is that if R is less than S, then for n very large, TRT n is greater than or equal to TSTn. So what this is saying is that there's an asymptotic equidistribution, but there's also a bias. The way this is done is the circle method and lower order terms. However, what I'm curious about is if there are combinatorial proofs of similar results and how they would happen, because it seems very, very difficult from what I know. The methods are completely analytic and based on generating functions. And it feels like there should be a combinatorial interpretation of this object. And there's an even better question related to representation theory as well, where instead of summing over all partitions, choose partitions where no part is divisible by k. It is exact same sum, but sum where no part in the partition, so say like no lambda j is equal to k. So I usually denote this by dk cross rt. And so equals the sum lambda n for all lambda j k does not divide lambda j of this same expression here. I'm just going to write it over time. And the same equidistribution holds. However, the biases are completely different. And in fact, they depend on the multiplicative structure of k and t mod each other. I can show you a bunch of interesting tables later. But what I really want to find is a combinatorial interpretation of these stacks. And I can't find one, essentially. And I can't find a combinatorial proof of any of them. So that's kind of what I'm thinking about and have been thinking about for many weeks.
So each lambda j is congruent to R mod T.
Yeah, so you count all the parts among all partitions of n, which are congruent to R mod T.
Okay.
And you get this asymptotic equidistribution, but a bias. And I'm curious if you could prove that bias combinatorially. So I don't.
And then have you tried to do a simple case like t equals 2?
Yeah, I have no luck.
Okay.
I'm not a very good combinatorialist,
Okay,
especially
okay,
for
okay.
partitions.
Because then you're just looking for even versus R.
Yeah. So this is the theory at least.
Yeah. Okay. So you said that an inequality method is proven, right?
Yeah, for large n, this is proven. Yeah,
Oh, for
this is
large
all
n,
proven.
proven.
But it's analytic, and I wish there were a combinatorial proof because
Okay,
this
so-
feels so.
Okay, so you're trying to do two things. One, you're trying to find a combinatorial proof for that.
Yep.
inequality. And second, you're trying to find like a combinatorial interpretation of that d cross function.
Yeah, so this one is the same function, and I know exactly what the biases are. They're
Sure.
not something you can write down simply. But I don't know a combinatorial interpretation of those biases either. This one is more interesting. They're much more structured than this.
Sure.
So,
When you wrote, no, lambda j is exactly equal to k. You got
yeah,
it.
sorry.
Okay,
This is-
okay, so that's the same stuff.
Yeah, this is over here. Sorry.
You know, as an aside, if you want to look at your analogs of like Waring's problem, and I want to know how many ways can I write something as a sum of, k summings. You can do this combinatorially. You can also do it analytically. The combinatorial one is very nice, but it doesn't generalize to if you wanted to write it as a sum of squares. And for something like that, you really need to then switch to the analytic perspective,
I want a combinatorial perspective on this because
Right.
it's,
or at least in some cases.
yeah, at least for this one. I doubt you could do it for this one. And
Right.
there's a good reason to doubt that you can do it for this one if you'd like to talk to me later. Yeah.
And do you have any results in the thing by Beckwith, and I forget her collaborators, okay, on how much the bias is? Is that-
Yes,
is it like a lower
there's an,
power
there's an,
band, is it log?
there's an exact, like, asymptotic. It's pretty, yeah, it's very good.
But it's, do you have a power savings?
How do I say? Here it's a, yeah, linear, shoot, I can't remember the exact
Okay,
number.
right,
I can
okay.
pull it up in minutes,
Okay.
but yeah.
Okay. All right. Any other comments?
It's not power savings, it's a constant on the coefficient.
Okay. All right, let's think again. All right, does somebody have something else they want to present, either from their talk? Excellent. So remember to state your name clearly for those in Zoom land.
Oh, sorry, I should have done that.
The last problem was given by Faye Jackson. I should know your name by now.
Obviously, this is going to relate to circles, right?
State your name.
So,
State your name.
Bruce Bowman from University of Delaware. Thank you. So if you look at this line and you say this is 1 minus x and this is x, and this is 1, then 1 minus x over x equals x over 1. Is that right? And so you get 1 minus x equals x squared, which goes to x squared plus x equals 1. Is that correct? So you can look at this in terms of a circle. I didn't want to think you had forgotten about circles. So if the circumference of a circle is 1, then what you got for the circumference of the circle, you could say this is x squared and this is x. Okay. So if you go to the eraser somewhere, oh, here it is.
Or you mean opposite, you did x, what would be x, oh, x.
Yes, because x is less than 1, so x squared is less than x.
Oh,
Okay.
Okay.
Am I okay so far? So if you go to the Fibonacci P numbers, you would have the same line, but it'd be 1 minus x over x equals x over 1 squared. Okay, and so you get 1 minus x equals x cubed, and then you get x cubed plus x equals 1. So then you could say that you get your circle and you would have x cubed and x if the circumference is 1. So my question is, this has been well studied in terms of Fibonacci numbers in 2 dimensions. How would you turn something like this into a 3-dimensional model? You got an x cubed. I mean, could you turn this into a sphere or an ellipse or some sort of geometric figure?
You just,
I mean, you got x cubed. I mean, could it be? I mean, sphere has it's a cube function, right? The circumference of the sphere. Yeah,
That's right. If I understand correctly. So what you might want is, you want to know sort of, if I'm remembering from your talk, the reason this is kind of relevant to you is you want these angles, right? And they're
yeah.
relevant to-
So in the Fibonacci world in phylotaxis, this is the divergence angle, which is all I talked about when I talked. But here you've got the divergence angle that's a cube. Could you have some sort of a, instead of a sunflower capitulum, could you have something that's a three-dimensional?
Yeah, so to me, the first thing I try and do is, if I'm trying to do that, is instead of taking a line and starting from a line,
Yeah,
as my ratio, I try and make the initial problem, like the initial conditions of the problem, two-dimensional and get a three-dimensional output. Like
So you
that
would-
is-
you would have,
I might take like a cone intersecting a sphere.
Yeah.
So,
I don't know.
so if you drink a lot of wine later tonight, that will look like a sphere. And then what you can do is you can have like a cone coming out, and the generalization of a radian is the steradian, which is,
Okay.
you know, like a solid angle. And maybe you could try to have like the surface area of that patch, you know, either
Okay.
your x squared or your x cubed, something like that. You know, if you want to try to come up with something geometric.
okay. I was wondering if you could just have your, to begin with x equals y, which equals z. And have the cube form, just if you know what your x is, you would have a sphere form to begin with.
Right.
But the other thing that's interesting about this is that, how do I describe this? You can also, you can also divide this into something that is one. You can have this be a branch, where this is one and this, I forget what it is. I think this, but the ratio of this would be x over 1 would, this would be x squared. I might be wrong, but you can look at the Fibonacci numbers as branches. So you actually have three, you could have maybe three coordinates or something.
Right.
Yeah,
And I think that you were saying maybe take a square or rectangle and
Yeah, yeah.
divide that.
Yeah, try and divide it up into different ratios.
Right.
You start with a two-dimensional problem and then it's out of two.
So you start with maybe, you want to start with a square?
I don't know how to divide it up.
Right, and then just you have some kind of division like this.
okay.
And so you can have, you know, here's maybe your x squared, and here's your x, or maybe here's your x cubed, and here's your x.
So you turn it into like a three-dimensional rectangle or something? Or
Yeah, so you start with a rectangle, and the hope is that by starting with a rectangle instead of a line, you can get a sphere and input instead of a circle.
Okay,
Same idea.
okay.
Yeah,
Thank
so,
you.
I don't know. That might be relevant.
We can do one more problem. Does anyone have one more? Okay.
Here's my,
No, it's from my. And I will say my problem is small. Oh, yes. Probably a good problem, but you left the board in a good state to speak. So that is bonus. You get extra grace.
I get minus space.
Yes.
Oh,
Name for the recording.
Rigo Flores.
Yeah, it's 7. Okay. We do that. Inflation is at the Fibonacci. index.
That's right.
Well, they used to be going at 60%, so you go.
Okay, this is the idea. So, so if we add these two, this is prime.
We have this two. This is prime. We have this two. This is prime. If we are at 11, 18, this is almost 8, right?
Wait, no, 13. The next one is 21.
Or is it?
Oh, you skipped 8. You skipped 8. 13 is 8. 13 is 8.
18 and
I'm going to start.
is 31.
Wait, but this should be 8.
Okay, so it's 8, 96. So how many primes are there of this form? Are there infinitely many or just finite?
And when it's, and what you're talking about here, just to be clear,
Oh, okay. This
is
is
you're doing, say, Ln plus
uh,
Fn minus 1, right? Or Fn plus 1. The index is 1. Right? Okay. So are there infinitely many?
primes of the form.
Right. So this would be, a great thing to do some numerics on. So we've got a couple of people who are really good at writing code, but just be very careful because numerics can be misleading for small values. And since this is being recorded, this is my chance to say one of my favorite examples. My students should know this by now. I will prove using numerics that 40% of all integers are prime and 20% of all integers start a twin prime pair. Can somebody give me I see some skepticism. Okay, can you give me the primes up to 10?
I'd like you to go to.
No. You were skeptical. Give me the primes up to 10. Yes? Yes? All of them up to 10. I mean, if you're getting tired, we could have somebody help. So notice 40% of the integers up to 10 are prime, and then 3 and 5 both start twin prime pairs. So 20% of integers start twin prime pairs. Now let's go up to 20. Can you give me, I know this is hard. 11.
17. 1996.
Yes, it's taking a long time, so we're going to stop here. We're not going to gather any more data. And we see that we still have 20% of all integers starting the twin prime pair, and 40% of all numbers are still prime, and we've doubled the range. So for something like this, the question is, what's the correct scale to be looking at for problems like this, especially given that these are exponentially growing? What's the right scale in terms of how far do we have to go before the data starts convincing us? For primes, I'm not convinced, going up to, 20. I do some work in elliptic curves where the key factor is the log of the conductor. And so even if the conductor is of size, 10 to the 20, the log of 10 to the 20 is still quite small. So if anybody's interested in writing some code, it would be very interesting, to report back on Friday, does this seem to persist? If you look up to 100, 1,000, 10,000, 100,000, what percent of the numbers, the indices n are going to have ln plus fn plus 1 prime? Mathematica is slow, but it has these functions predefined. All right, so I think this is a good place to stop the problem session. So thank you everyone for coming and for proposing problems. We now have a break until the break ends, at which point we will then have the 3 parallel talks going on. So that should be at 4:15. Yes. So yes. Well, I want to make sure that I'm mathematically accurate. And so I will rename the break rooms based on the titles of the 3 talks so that you can figure out which room you want to go to. Well, I can't have the break going until before it ends. Yep. I've got things under control. I have things under control. See you tomorrow. Wait, you're not going to the banquet?
Oh, sure.
Okay.
Oh, yeah.
Okay, just, yeah, there's alcohol. All right.
You got small parts. Should be kind of small parts.
Okay, people in Zoom land, if you can hear me, we will be moving to the 3 different breakout rooms, and I will keep adjusting the title as we go.
So Steve,
Yes.
you're still recording. If
Oh,
you,
thank you.